All right, so good morning, everyone. Welcome. So today we'll be talking about Polaris. So Polaris is a open source benchmarking platform to evaluate the performance of machine learning models. If you're familiar with Kaggle, it's a little similar to Kaggle, except that we built it from the ground up, specifically to support the challenges that we face in drug discovery research. I realize that I'm talking to a primarily data science audience, not a drug discovery audience, so I don't want to spend too much time about the drug discovery aspect of it all, but I'll promise you we'll get into some interesting data science topics as well as we face some challenges as we set out to build this platform that can sort of support the wide variety of data sets that we encounter in drug discovery. Specifically, we'll be talking about Zarr. So Zarr is an open source project, a data format for storing n-dimensional arrays, which proves very helpful in this project. I also think it's worth noting that we'll be talking about Polaris, which is this benchmarking platform. We'll not be talking about Polaris, which is this data frame library. Looking at the schedule earlier this week, I figured that may have been a little bit confusing. I hope I let no one astray. If I did, I hope you stick around. We'll be talking about some cool topics. So yeah, that's all. So this is what we'll be discussing today. So we'll start off with a bit of an introduction, just to make sure that we can set the stage for the rest of the talk, make sure everyone sort of has a basic understanding of what machine learning for drug discovery is all about. After that, we'll be talking about the data format. Specifically, we'll be talking about some of the considerations we had as we were designing this system. Then we'll talk about how we actually ended up implementing data sets within Polaris. And finally, we'll discuss or touch upon some of the challenges that we encountered that maybe were a little less expected, but nevertheless very important. Okay, so first things first, drug discovery. So drug discovery is a whole topic on its own, and we won't have time to get into all of it. In short, it's the process of bringing new medications to the market and to patients. The main point I want to bring across today is that this is a very time-consuming and expensive process. So a recent study estimated the total cost of bringing a single drug to market to be about $6 billion United States dollars. This whole process is also estimated to take about 10 to 15 years. I do think that number by itself is a little misleading because it does account for all the failure along the way. So typically these drug discovery companies, pharmaceutical companies, they don't just run a single drug discovery program. They'll run multiple of these programs in parallel. And the vast majority of these programs will fail somewhere along the way. And that failure is very expensive. So if you look at the cost of actually just bringing a single drug discovery program successfully from start to finish, the cost is actually a lot lower. It's only about $100 to $200 million only, pocket change, right? But you can see that there's quite a big gap there. And that gap can be explained by the high failure rate, as I was already hinted towards. So the failure rate of this entire process, the entire drug discovery program process, is actually around 99%. So if you start 100 drug discovery programs, you'll expect only one will actually lead to a new medicine. Now that's already a very high, astonishing number if you ask me, but I think the number that's maybe even more crazy is when you talk about the failure rate once you reach the clinic. So once you reach the clinic, the final part of the drug discovery process, you're confident that you've got a drug that works, you're ready to test it in patients. At that point, you've spent hundreds of millions of dollars to get to that point, and then still the failure rate is about 90%. So that 6 billion figure that we discussed earlier, that sort of accounts for all of the programs that didn't make it. So you spend a lot of money to just get a single drug to market. And the whole promise of machine learning is to make this process more efficient. So we can get better medicine, we can get more medicine, we can get cheaper medicine, and all of that really holds the potential to radically improve lives across the board. All right. I think it's also worth noting that drug discovery is not a single problem. It actually spans multiple problems across chemistry, biology, physics, computer science. And I think you'll find that it's quite a scattered community. So typically these different sub-communities, they don't really interact with each other a lot. They tend to have their own standards, their own tools, their own way of communicating. And that makes it quite difficult to transfer skills. Once you're working on one problem, it's not as easy to easily switch to another problem within the same community. I think to an extent, that's to be expected. As a machine learning scientist or a data scientist in general, I think if you want to truly impact a problem that you're working on, you're expected to spend some time understanding the problem and sort of the intricate details of it. However, one thing that's very different in drug discovery than in typical applications of machine learning, such as computer vision or natural language processing, is that these problems are not intuitive, right? If I build a computer vision model, to some extent, I can quite confidently look at the predictions of that model and tell you whether this model is doing a great job, a not so great job, or somewhere in between. This is not the case for chemistry or biology or physics, typically, right? Like, you need a PhD to even sort of build up some sort of intuition. And you just, as a machine learning scientist, you cannot be expected to have that level of expertise within a reasonable amount of time. At the same time, benchmarks are a really important tool within the machine learning community, right? They tend to drive and inspire progress. So this is leading to a bit of a weird situation where benchmarks are really important on the one hand, but on the other hand, it's inherently difficult to propose a benchmark because it requires this interdisciplinary expertise that not a lot of people have by themselves. And all in all, sort of the observation we had is this is creating a gap between perceived progress, like we're super excited about machine learning, it's changing the world, we're solving drug discovery, versus actual impact in real pharmaceutical companies. So I'm a computer scientist myself, and just to illustrate this with a bit of an anecdote, like when I started working in drug discovery, I did everything that I was taught to do, right? So I found the data set, I split my data, I did some sort of like basic data set creation, removing duplicates, I did my modeling, I optimized my hyperparameters, I did everything I was taught to do. And at the end of that process, I came out and I had a 1% improvement over the state of the art, right? Like, hooray, we solved drug discovery, life will be so much better now. Unfortunately, it's not that simple, right? Then I would show those results to my colleagues and they would come up with all these annoying questions. They would ask me, what's the statistical significance of those results? Or they would ask me, what's the applicability domain of your model? Those compounds, they look great, but there's no way we can synthesize them. How did you handle stereochemistry during dataset curation? Could you actually explain the predictions to us? What's the decisional impact of this change in this improvement? And finally, even questions that maybe as a software scientist, I never thought would lead to problems, but questions such as like, how do I install your model or how do I actually use it, right? All of these things become important. And I don't expect everyone to sort of understand all the questions I put on the slide here, but I think that's precisely the point. I think you cannot really be expected to understand all of these considerations without having actually been part of like a very interdisciplinary team that does the work in a real world setting. Okay, so this is where Polaris comes in. So Polaris is a open source and open science initiative to improve the benchmarking standards in drug discovery and ML-based drug discovery. And specifically, we're taking a two-angled approach. So on the one hand, we're working together with a multidisciplinary and a cross-industry group of partners. And the goal with this sort of more scientific direction is really to come up with beginner-friendly guidelines that just simplify the adoption of best practices within drug discovery. So if you want to do dataset creation, what are sort of the common mistakes you might make? What should you be paying attention to? This is how this project started out, and I still think it's a very important aspect of it. But one of the things we realized sort of along the way is that if we're going to be doing this and we come up with a very shiny paper, we publish it in something like Nature and everyone is super happy, even if we manage to accomplish all of that, we weren't sure if this was going to live, if this was actually going to be adopted by the community. So that's where sort of the second angle comes in, and that's the main focus of today's talk, is we decided we also needed to follow up with open source software to really simplify the adoption of these best practices. And we centered all that open source software around this product that we call the Polaris Hub. And the Polaris Hub, again, is this benchmarking platform, something similar to Kaggle, but then specific to drug discovery. Okay, so the data format. So we set out to build this benchmarking platform. And one of the first things we started thinking about is like, how can we actually implement data sets within this platform? And I think the important thing to note here is that there's a wide variety of data sets. They come in all sorts of different shapes and sizes. And what we set out to do, the challenge that we gave ourselves is, can we come up with a way to unify all of that in a single format? There's a variety of reasons for this, but I think it's, maybe for the sake of this talk, I won't get into too much detail there, but I think that was the goal that we set ourselves. Can we unify the variety? So what variety am I talking about? Well, for example, there's an enormous variety in terms of modalities. So depending on where you're working in the drug discovery process, there's different data formats that you're using that represent different sort of biochemical entities within different levels of abstraction. So if you're working on the cell level, you might be working with microscopy images that's saved as PNGs. At that point, you can probably apply typical computer vision learning techniques. But if you zoom in a little further and you start working with proteins are three-dimensional structures. These three-dimensional structures are typically saved as PDB files. And then if you zoom in even further, you might be thinking about working with molecules. Molecules are also three-dimensional structures, but they are not saved as PDB files typically. They are typically saved as SDF files. And then maybe you want to abstract away that 3D structure. Maybe you just want to be thinking about the 2D structure. In that case, you're essentially just thinking about the graph that a molecule is. These are typically saved as small strings, although there's many other formats by which you could do so. So there's just a wide variety of data modalities that are of interest within drug discovery. And this posed a bit of a challenge. But I think one realization we had somewhere along the way is that actually we don't really care about these specific file formats, right? PDB files serve a very specific purpose to be used by mostly biologists. We're not building for biologists, at least not primarily here. We're building for machine learning scientists. We want to simplify the machine learning process. And machine learning, in some way, shape, or form, as input to your machine learning model, you typically work with these n-dimensional arrays. So what we need is we don't need a way to save these very complex file formats and have like different file handlers and like read and write operations. No, we just need a way to save the ND data that you would typically feed as input or as output or expect as output from your machine learning models. Then the second axis of variety is that data sets come in all sorts and shapes and forms within drug discovery. I think in some drug discovery applications, the cost of data acquisition is very high. So you end up with data sets that maybe only have about 500 molecules. You can save those in, like, depending on how you save them, but like just a matter of kilobytes at that point. In other applications, data generation is a little more cheap. So for example, in phenomics, that's microscopy imaging. You have a lot higher volume of data. So there you typically are talking about terabytes of data. And we wanted to come up with a system that could support that range of data set sizes. And another important consideration is that, again, we're building for machine learning. So we wanted it to be simple to provide a very performant data loader based on this data set that we come up with, right? And that's actually more tricky than it may seem, because in machine learning, you typically shuffle your data and randomly access it. So we needed to come up with a way to effectively randomly access parts of the data set. And finally, we also wanted to lower the barrier of entry to the platform. So we realized if we want this initiative to be successful, we need a lot of people to adopt it. For that to work, we need it to be simple to convert your existing data sets to the platform, upload them without having to learn a very new language and a new tool. Okay, so if we sum that up, we were looking for an efficient format for storing ND arrays. We wanted it to be able to scale up to terabyte-sized data sets. We wanted efficient data access for machine learning, and we wanted it to be easy to migrate existing data sets to this new format. And what we landed on was the usage of Zarr. And Zarr is this format for storing ND arrays that is also open source and I think also sponsored by NumFOCUS. I was surprised to not see them here. I think it's an awesome project. So if anyone in the audience is actually from Zarr, you're doing great work. Keep it up. But yeah, hi. Yeah, so I just wanted to, I felt like it was worth diving into that topic, even though I'm not myself associated with Zarr in any way, shape, or form at this time. Okay, so Polaris datasets. So give you a basic understanding of Zarr, the idea is as follows. So Zarr, you have a n-dimensional array. That's your starting point. And these can get very, very big. So for example, I just put a terabyte for now on the slide. The cool thing about Zarr is that it lets you chunk that data set. And the chunking is actually very flexible. So in this case, I'm just showing these like nicely formed cubes, but you could do it along any axis in any sort of chunk size. And those chunks, they are a lot smaller. So they are only, for example, in this example, they're only about 1 gigabyte. Now, the cool thing is if you want to access any data point within that large terabyte-sized array, you really only need to be able to, you're going to be loading the chunk to memory. You're not going to be loading the entire data set to memory. So that allows you to quite effectively traverse these very high dimensional and large arrays. But then the additional layer that Zarr adds on top is that it also adds support for compressors. So now that you have your chunk, and that chunk is maybe 1 gigabyte, you can compress it all the way down to maybe a couple of megabytes. And that may be optimistic, depending on your use case, but you can imagine that actually working out. And the cool thing is you then compress it, and you once you load it, you decompress it again. And why that's cool is because it allows you to sort of trade off between the performance penalty you get because of the decompression and the compression, while also improving the speed by which you can transfer this data across the internet. So you can actually host this terabyte-sized file data somewhere in the cloud. And whenever you need to access part of it, what you do is you just pull that compressed chunk down to your local machine, you decompress it, and then you can start working and operating on it. All right, so how are we using this within Polaris? So within Polaris, we are starting off with the assumption that the data set is like a tabular structure, where each of the rows is one of your data points, and each of the columns is one of your measurements for that data point. So for example, if you're working in drug discovery, you might have a column with all your SMILE strings, and you might have a column with the HOMO-LUMO gap, which is a particular property you might be interested in predicting. You can also have additional metadata in this data set. So we don't put any constraints on the data you put in the data set. You could put additional information in there that you don't directly see being used within drug discovery, but nevertheless want to provide. And then what we do is each of those columns is associated with annotations that contains additional important metadata that you want to have access to if you're actually curious about using this data set in a real-world drug discovery program. And then we also annotate the entire data set with, yet again, additional metadata. And that metadata, that's an important part sort of like of the scientific angle that I came up with earlier. There's specific things you just want to have documented, and we wanted to provide a place to do so. Yeah, I won't get into too much detail, but just know that it's there for a specific reason. But now the question is, what if we have more complicated data that doesn't sort of neatly fit within this tabular structure? So for example, in conformer, which is the 3D structure or one of the 3D structures of a molecule, this is all the 3D coordinates for each of the atoms. Maybe there's even some additional information in there that may not be effectively stored, or that won't be effectively stored within this tabular data format. So what do we do in that case? We again have an annotation. In this case, we are specifically setting this isPointer attribute to true. So what that will tell the system is that the data in that particular column is not actually the data itself. It's rather a reference to where that data can be loaded from. So for example, I just put some string identifiers in here telling you from the conformer group, from the data array, take the very first row within that array, like index the very first axis. And then the question is, where is that data then actually stored? Well, that's in Zarr. So sort of Zarr is used as sort of this overflow where anything that doesn't neatly fit in the data frame can be stored in this large Zarr array. This does make one assumption. The assumption it makes is that we can load the Parquet file at all times in memory. So we're sort of making this assumption that it will be at most a couple of gigabytes. Now, I thought that would be reasonable, at least for the sort of short term. But actually this week we had a request from someone and they wanted to upload 3.6 billion rows of data across 7 different columns. And if we would very much like optimize sort of this reference that we have, and we would use on-site integers, 32 bits, we ended up with about 100 gigabytes, which no longer fits in memory. So we might have to rethink this approach, but this literally happened this week, and I have some ideas on how we can do it. I think Zarr will be an important part of it. But yeah, that's just a little side note here is that it's not as flawless as we maybe hoped it would be, at least for the foreseeable future. Okay, I think there's a lot more to like about Zarr. I think there's two things that really stand out to me. I think on the one hand, it's really, really flexible. So Zarr really just specifies a data format, but that format is language agnostic. So there can be multiple implementations in different languages, programming languages. You also can use different storage backends. You can use different D types. There's a lot of like compression algorithms that are already supported, but if you need another one, you can add one yourself. So there's a lot of flexibility there. I think another thing that really stands out to me is that they seem to be really good open source citizens. They have a really nice governance structure in place. They also integrate nicely with other tools such as Dask and Xarray. So if you're interested in sort of high volume data workflows, Zarr just is a nice tool to be working with. So this is, in the end, the high-level API that we came up with. So I'm actually pretty proud of this. So we managed to come up with a system that, independent of what the data set is that you have stored in your background, with just a single line of code, you can load that data set. Then with just a single line in code, you can split that data set in a train and test set, and you actually have a pretty performant data loader that you can directly use. So these train and test objects are data loaders that with one line in code, you can integrate with PyTorch or TensorFlow or Keras or any other machine learning framework of your choosing. So then once you have those data loaders, you can train your model. This is really where machine learning scientists can work their magic. They come up with a way to predict the labels of the test set. And then again, with one line of code, we can evaluate the predictions. And with yet another line of code, we can upload those predictions to the hub. And all of this is, the current state of doing things is that people in drug discovery, typically benchmarks are hosted in these GitHub repositories. And if you want to upload your results to it, you'll make a pull request showing your results. You're hoping that someone will review that within sort of the foreseeable future. Probably not. So things become stagnant quite quickly. And the cool thing about this is that it's really meant to be a community-run platform. So you can upload your results without us having to be in the loop. That all is an automated process. You actually can have your results be private. Then once you go to the hub, there's a UI. You can make them public at any point in time. So it's really like a community-run platform. There's no central point of failure. At least it's designed to be that way. Then I also mentioned it's important for us to lower the barrier of entry. So I think the important part here is that Zarr is cool, but if you're a drug discovery scientist or you're a machine learning scientist, you might not have worked with that before. So if you're expected to figure out all the details of Zarr before you can upload a data set, that may be too much to ask. So what we ended up doing is creating this dataset factory class, which allows you to register converters for the common file formats within drug discovery. And with just a couple lines of code, you can convert from these typical file formats to Zarr and upload to the hub. So everything is working as expected. I would say, yeah, I will add that this is in beta. So we have support for some first converters, and we're actively working on adding support for more. But if you spot any errors, maybe to be expected. But we're working hard to improve that. All right, so then finally, I just wanted to touch upon some challenges that we encountered that we maybe didn't expect, but that turned out to be important. So first of all, data access. So I mentioned it's important for us to have very performant data access. And I mentioned that there's also this difficult pattern of like, you're randomly sampling your data set. The thing within Zarr is that things are saved as chunks, and those chunks can be compressed. So if you try to access a very specific row, what you'll have to do is you have to make a copy of that chunk that row was in, and then you have to decompress that chunk before you can access that row. So that's quite a big performance penalty for just accessing a single row. If you're doing random access, chances are after you've accessed that single row, you'll throw away all the other data that you have in that chunk because you're going to be randomly sampling to another part of the data set. So we looked into optimizing this, and again, I think here the flexibility of Zarr was a big help. We really had a lot of tools at our disposal to try and improve that performance, and there were a couple things that we felt really helped. So on the x-axis here, x-axis, I'm showing the size of the data set, and I split it in sort of 3 portions. So we'll be talking about data sets that fit in memory, in local memory. And we'll be talking about data sets that no longer fit in memory, but that you will fit on local disk. And finally, we'll be talking about data sets that fit not even on your local disk, so you'll have to store it in cloud storage. And on the y-axis, we'll be looking at sort of the performance, the time it takes to access data. And I should say that y-axis is a little arbitrary. It's not meant to be absolute, it's just to indicate relative improvements. So for the in-memory case, what we found is that the best thing you can do is sort of load the entire thing into a NumPy array and work with that NumPy array from there on forwards. That was a little bit of an anticlimactic conclusion maybe, but yeah, NumPy has been heavily optimized to do that very specific thing, and Zarr just isn't meant for this use case. Nevertheless, this wasn't hard to do at all. It took us like 1 line of code, I think. So like, it wasn't a big problem, but yeah, in the end, we just found that when you're like, when something fits in memory, the best thing you can do is just load it to a NumPy array. Okay, so what if you can no longer fit it on memory, but you store it in a local disk? Well, here we found that one thing that really helps is rather than chunking multiple data points together in a single chunk, what we did is we stored a single data point per chunk. This could lead you to lose a bit of the memory optimizations, right? Because if there's repetition across data points, which is to be expected, you could expect to compress that data and have a bigger performance gain. So this is a bit of a trade-off you have to make. Maybe it's worth not doing this, because then it means you can store it on your local disk rather than in cloud, but that's a trade-off people can make. But what we found is at least one of the ways to improve performance is by just having a single data point per chunk. Then another optimization, which is a little more straightforward because it sort of works out of the box and it works always, so it's not really a trade-off you're making, is to use memory mapping to store the files that Zarr creates on your machine so you can more quickly access them. I think this again speaks to the flexibility of Zarr. Like, we are able to implement our own storage backend, so if we want to use memory mapping, it's really easy to do. And then one other thing you can do is just disable compression altogether. So Zarr supports compression, and it supports many different algorithms of doing so, but it doesn't require you to use compression. So this is again a bit of a trade-off. I think actually a lot of these decisions you can make are sort of on this space-time trade-off topic, which is more broadly known to be a balancing act that you typically have to do in applications. And for cloud storage, what we found is that instead of completely randomly sampling a data set, one thing you can do is you can use these out-of-core machine learning algorithms. So that means that once you have a chunk loaded into memory, you make the best use of that specific chunk. So you make sure you use all the data that's in there before you discard it and move on to the next chunk. I should also say, and that's a little asterisk I put there, that these are optimizations for common use cases. I'm sure that if there's a specific use case you have, you can optimize things further. And one of the goals that we have is to make that possible. But we want to have a performant data loader sort of that works out of the box. And that was the main goal with these optimizations. All right, so another thing that we ran into is that we cared a lot about access control. So we wanted it to be possible for people to have private data sets. That means that we need to have some sort of authentication layer in front of our storage endpoint. And what we were using is we're using these signed URLs. However, Zarr is a folder-based format, so we couldn't easily create signed URLs for a folder. So what were the solutions we tried? Well, one of the things we tried first is you can actually store a Zarr archive. By default, it will store it as a folder, but again, it's very flexible. And one of the options it provides out of the box is to save everything into a zip file. Zip actually supports random access as well. So that's one of the ways you can create a file and create a signed URL for that file. This worked, but we were worried that we were sacrificing some flexibility that we may want due to some of the other challenges that started arising. So the next thing we did is we actually implemented a custom FS-spec specification that allowed us to traverse the cloud bucket and just create signed URLs whenever we needed them. That worked, but it came with a bit of a performance penalty because we had to do multiple requests whereas normally that would just be a single request. And also all of the optimizations that had been done on accessing the cloud bucket that we were using, we had to re-implement them ourselves or sort of cleverly reuse them, but that was just proved to be a big performance hit. So what we're actually working on now, and this is looking like it will work, is we figured out we can create actually a downscoped admin token for our bucket that will give access to a specific prefix, so a specific directory within the bucket. And that allows us to just use the heavily optimized FSPEC implementations that are out there. So we don't have to implement these ourselves. We just use different credentials that have been scoped to be limited to a specific bucket. Okay, and then I think this is the last thing. Yeah, the last thing we came up with is that we wanted to make sure we can guarantee data integrity. So data integrity is also very important. For example, we wanted to know if Zarr is saved as a directory by default, and I've rendered sort of a simplistic figure of what that directory might look like. It means that we're not uploading a single file, but we're uploading multiple files at once, and we wanted to know when we had successfully completed that upload. We also wanted to make sure we didn't lose any data along the way because we're uploading quite a lot of files, so we wanted to just have a check in place to do data integrity. And again, we had this question of okay, how do we actually come up with a checksum that takes into account an entire directory and all of the subfolders? And luckily, we didn't have to do a lot of thinking here ourselves. A little bit of thinking, but not that much, because there already was this very cool package out there called Zarr checksum, which essentially has a nice tree traversal algorithm that starts at the leaves and then sort of propagates those checksums up the tree until there's a deterministic checksum that works for the entire directory. And that's actually quite fast. So we could leverage that to implement the checksum algorithm that we have. All right, so with that, that's all I have to say about Polaris for today. Thank you all for listening. So if you think any of this sounds interesting, we would love to hear from you. I think there's a lot that we can learn from all of you. One of the best ways to get in touch is through our GitHub. We also have a Discord community if you're interested in joining that. And if you're curious to see what this platform actually looks like in practice, the website is live. You do need to create an account for the time being, but we have a PR open to enable anonymous access, so that should be there within a week or so. And you can find that on polarishub.io. Yeah, with that, thank you, everyone.